Okay, so our topic for today is all about model evaluation. Okay, so basically we have covered the first five phases of your data science methodology, and that is your data understanding phase, number one, and then data preparation, EDA, exploratory data analysis phase, the setup phase, and then the modeling phase. Well, a little bit of the modeling phase, but no, so far, since we already have a model, we haven't examined them thoroughly, right? And we really don't know that the models that we have built are any good. Okay, so that is, we have not evaluated the usefulness in making such predictions or the predictions of your model. So take note the difference between the evaluation process as well as the validation process. Now, for the model validation, it's actually simply making sure that the model results are consistent between the training and the test data sets. Okay, but the model validation does not tell us how accurate the models are, or what are their error or whatsoever. So for measures such as this one, we need to take turns in terms of the model evaluation. Since the only models that we have learned so far is actually the decision trees for this topic, no, we will be focusing also more on the C5.0 algorithm. No, it's also a decision tree of some sort. Now, we will develop a classification evaluation measures later on. So for that case, no, where we will be needing or we will be doing a binary target variable. So in order for us to be able to apply these measures, no, we will learn, put into perspective what are the things that we really want to pursue, no, in terms of creating an evaluation measures. Just like this one, ano, there's an actual category and then there's a predictive category of some sort. No? You can actually see there on the table. No? So supposing, no, for example, that we're trying to predict an income, okay, an income of a person or probably an employee of a certain organization. Okay, so we're trying to predict the income, and then we'll just have to put into a binary variable, no, of some sort, whether the income is actually high or whether the income is actually low. So that's only 1 and 0. So we could denote that high income is actually a positive one, and then a low income is actually a negative one. So that will be probably 1 or 0, some sort. No? Now the classification model that we need to do is more on evaluation measures. No, we will be learning different functions of the entries of a contingency table, just like this one illustrated on the PowerPoint. And then take note also, by convention, the actual values are actually represented by the rows, while the predictive values are represented by the columns. All right. So the upper left cell in the table represents the numbers of records where the model predicted a negative response. Okay, that's for example. And then the actual response value is actually indeed negative, making this prediction a true negative. Now, the cell below, as you can see there, actually represents the number of records where the model predicted a negative response, no, but actually the response value was a positive. So which makes this prediction a false negative. And then the other cells are similarly defined, as you can see there on the table. So to put this into perspective, okay, for example, here you have their actual category and then your predicted category. And then here is 0 and 1. Okay, so anything 0 and 0. So for example, the actual value is 0, but the model actually predicted 0 as well. So it means to say these are true negatives. Okay, predicted 0, actually it's 0, so that's true negative. Okay. Now, when you have an actual category of 1 and then you have a predicted category 0, it means to say that all of those entries are actually false negatives. So predicted 0, actually 1, so that's false negatives. Okay. So on the other hand, if you have false positives, no, you have predicted 1, but it's actually 0. You call that false positives. Okay. Now, when you have predicted 1 and then actually you have 1 as well, so that's true positives. And then for the total, so that the TPN and the TPP, these are actually total of all the predicted negatives and all the total of the predicted positives. No? And also, there is a column here that you can see total actually negative. These are the sum of all true negatives and false positives. And on the other hand, the TAP, or what we call the total actually positives, these are the sum of all false negatives as well as the true positives. Okay, and then you also have the grand total there. All right. So I think it's fairly easy to comprehend this one. Ano? Okay, the contingency table. Okay. Now here you have your notations. Okay, the notations is actually based on what I have discussed earlier on the previous slide. No, so you have your TN, FN, FP, and TP represents the number of true negatives, false negatives, false positives, and true positives, respectively. No, so this is actually based on the contingency table. So as you can see there, you have your actual category, okay, and then predicted category. So for 0 and 0, you have your TN, okay. So for actual category 0 and predicted category 1, you have your FP. For actual category 1, and then you have your predicted category 0, you have your FN. And then for the actual category 0 or 1, and then you have your predicted category 1, you have your TP. Okay, and then just have to put your notations there. TN, FP, TAN, the total, and then FN, TP, the TAP, GT, your grand total, and so on and so forth. Okay, so for your TAN is a total actually negative, which is the summation of your TN plus FP, okay, and so on. Okay, and the grand total, of course, is the summation of your TN plus FN plus FP plus TP. Okay, so that would be your grand total. Okay. Now, you just have to take note of these notations because most of the time, when you create your contingency table, you'll be referring all of those. By using the notation based on the previous table, no, we will be defining the set of classification evaluation measures. So the evaluation measures are the formulas that we're going to utilize so that we may be able to evaluate the model, okay, or the model that we'll be creating later on. Okay, so as you can see there, the accuracy actually represents the overall measures, no, of the proportion of your correct classification being made by the model. Okay, so the formula for the accuracy is TN plus TP over TN plus FN plus FP plus TP, which actually equates also to TN plus TP over your grand total. Okay, and then on the other hand, the error rate is actually the measures, is actually measuring the proportion of incorrect classifications across all the cells in your contingency table. Okay, so the formula will be the error rate, which actually equates to 1 minus your accuracy equals to your FN plus FP over your TN plus FN plus FP plus TP, or FN plus FP over your grand total. Okay, so like I've said, no, the accuracy is the overall measure of the proportion of correct classification. Since this is the accuracy of the model itself, measuring correct classification, whether the model is actually pinpointing towards a negative value or a negative result or a positive result. We're actually pinning down the accuracy of the overall measurement of correct classification. All right. So if you're actually classifying, say for example, an ambulance on a video scene, this is when you have a value in terms of accuracy, it means to say the value is more or less, or the measurement of how many times or how the percentage of your model actually detected an ambulance on a video scene. Okay. Now, the error rate is actually the proportion of the incorrect classification across all cells in your contingency table. This is the number of incorrect classification, a proportion given on each of the cells based on your contingency table. Now, take note that this do not distinguish between the various types of error or correct decisions. So later on, we will be applying the sensitivity and specificity formula for this one. Now, for the sensitivity and specificity, the formula for sensitivity is the number of all true positives, okay, divided by your total actually positives, okay, or TAP. So TP over TAP. Or sometimes, if you have another formula, TP over TP plus FN. Okay. Now, your specificity is actually the number of true negatives over your total actually negatives. Or the formula is actually TN over TAN. Or if you say TAN, TN over FP plus your TN. Okay, so take note that the sensitivity measures the ability of the model to be able to classify a record positively, while specificity is actually the measurement or to be able to measure the ability to classify the record negatively. Okay, so you're gearing towards the sensitivity is gearing towards all the true positives, and then the specificity gears towards the true negatives. All of those are actually the actual value, the ability of your model that you have created to be able to classify such records. Okay. Now take note that the perfect classification model would have a sensitivity of 1.0 or 100%, or also a perfect classification model would also have a specificity of 100% as well. But again, there should be a good classification model acceptance. And this is actually having a level of both sensitivity and specificity, which has a balance, a number in a way. Then of course, if you're actually gearing towards more on the positive, you're looking at the positive result of your model, your sensitivity should be higher, of course. It would be much appreciated if you have at least 80% or 85% sensitivity model result. On the other hand, if you're actually looking for a true negatives, you might be asking, sir, why is it that we need to look for a negative? Because there are some models that you can actually look on data which has a negative results. Say for example, you have an analysis, urine analysis, which actually look for cell that doesn't have any bacteria. So that's negative, doesn't have any bacteria at all on that particular urine sample. So you're actually looking for a number of true negatives. Okay, so it means to say that your model should be gearing towards a high specificity, not a high sensitivity. Of course, like I've said, if you're looking for a true negatives, you might want to have a higher value or a higher percentage in terms of specificity. But again, having a high specificity, like for example, 99% or 100%, it doesn't mean that you have a very good model. So like I've said, a good classification model should have an acceptable levels of both sensitivity and of course your specificity. Okay? But like I've said, no, the acceptable results should actually varies no greatly from domain to domain. Like I've said, what your model is actually looking for, or what is the thing, or what is the objective of your study, or what you really want to attain no, upon creating your model. Okay. Now, here, this is another one, which is what we call the precision and recall and the F scores, no, F sub beta scores, no. So, precision is actually defined as the records classified by your model as positive. What proportion are true positives? Okay, so the metrics actually addressing the question, the precision, and this is actually more on the field of information retrieval. Say for example, the precision matrix no answers the question, what proportion of the selected items is actually relevant? Okay, so this metric is often paired with your recall. Okay, so that's why you have your precision and then you have your recall, which is another name for your sensitivity. Okay, so it would be useful to combine the precision and recall into a single measure so that you may be able to know the harmonic mean. That's why you have the F sub beta scores. You have your F1, F sub beta 1, F sub beta 2, and so on. Okay, so the harmonic mean of precision and recall, these are actually equal weighted in the metric of your F sub 1. Okay, so meaning overall, no, the precision is more on the number of all positives, no, detected by your model, which is precisely detected, no, or classified by your model. And then your recall is actually the precision or the precise number. Well, we don't actually call it precise, no. It's actually the total number of all the negatives that accurately detected by your model. So that's what you call the recall part. Okay, so that's your precision and recall. All right. Now, there are several methods that you can actually use for model evaluation. Number one is to develop a model using a training data set and then evaluate the model using your test data set. That's why I have given you a discussion board. No? Why do we need to split the data set that we have? No? So I think at this point in time, you already know that there are variations of means and ways to be able to divide your data or split your data, whether it's 80-20, okay, or 80-10-10, or probably 70-15-15 or 70-30. So it actually depends on the requirements of the model. Okay, and of course there are cases wherein a lot of people gear towards what are advisable or what are the advices given on some of the previous studies, no, or some of the previous journals that you have read, no, while doing your model or while creating your objective. So it's very important to be able to at least know that, no, before trying to do a separation or division of your data set. But definitely for the training, it should have a higher percentage than of your compared to your test data sets. And of course, there are also cases where in training, testing, and then you separate another data set, part of your data set for your validation. So training, 70%, for example, 15% for the testing, and then for the validation of the model, you allot the remaining 15%. Okay. Now, for this part of the course, we will be using the clothing data, clothing underscore data underscore driven training data set, as well as the clothing underscore data driven underscore test data sets. No, we will be utilizing that. Of course, I'll be uploading that as well on Blackboard so that you may be able to at least utilize that. No, and then I'll be also uploading a separate Jupyter notebook so that you may be able to continue working, no, on the models, no, for this particular part of your data science methodology. No. Now, here there are three continuous predictors that we will try to take a look into. No, the days since purchase, the number of purchase visits, and the sales per visits. No, you can also refer that to the Jupyter notebook that will be uploaded later on. Now, there will also be a target variable, which is a flag, okay, which the response will be coded as 1 for positive and the response for 0 will be considered as negative. Okay, and then we will be developing a C5.0 model for classifying responses. No, take note that we will be creating several models, and then we will be doing comparative analysis for each of those models. No, the result, of course, of each of those models. No, and then we will be gearing towards the C5.0 model. Decision tree. It's a type of decision tree later on. Now, to be able to obtain the predictive values, like I've said, no, the 0 will be considered a negative response, and then the 1 will be considered as a positive response. Sir, you might be asking, why is it at 1 and 0? We will just be doing a flag in terms of responses. Remember, we are gearing towards, say, for example, a marketing campaign. It's actually a marketing campaign through phone or your email. So it means to say that if you're within the organization, you will be asking someone to be able to phone in your clients, no, using a phone or an email strategy marketing campaign. Okay, and then your model will be able to predict whether all of this or some or this particular client will be responding through the phone or email that you have done. We'll try to at least investigate whether all of our clients would actually do a good response or not. That's why we're actually creating, we will be creating a model. Okay, so it's only 1 and 0 for that matter. Okay, so of course, to be able to test the data, we will be comparing the predicted values for the actual response values. No, so as you can see there, there's a contingency table. Okay, the actual category and then the predicted category. You can see there 1 and 0 as well. Now, based on the data set, you can actually see there the true negatives, false positives, and the true positives. No, there are numbers there. Don't worry, because if you actually run your Jupyter notebook, you may be able to see the results as well, similar to what is being posted on the PowerPoint. Okay, so the values that we have right now there, the TN, the FN, the FP, and the TP, those came from the data set. Okay, you need not to worry. The true negatives is 9,173, the false negatives 1,396, the false positives 441, the true positives 544, and so on and so forth. So just just try to utilize the formulas that I've given a while ago, and then you may be able to compute the TAN, the TAP, the GT, the TPP, and then the TPN as well. All right, so based on the values that I have given or posted a while ago, take note that you have your TAN. Okay, the TAN is around 9,614. The TAP is 1,940, and the GT is 11,554. That will be true across any model because these are actual values and not the predictions. No. Now, the remaining number varies. No, the remaining numbers vary across different models depending on the predictions. No, so the result of the 8 evaluation measures are actually shown here. No. Actually, I just posted 5 evaluation measures. Now you can actually see there the accuracy of the model. The first model is about 0.84 0.8410, okay, which is the accuracy of the model 1. And the error rate is actually 0.15 or 15%, 16% more or less, no, in terms of the error rate. So as you can see, the first model or model 1 has a very high accuracy of about 84%. And the error rate is just about, 16%, no. Now, you can actually see there as well the sensitivity is about 2 to 28, no, 28%, while the specificity is about 95%. So from here, you would see that it gears towards negative values because of the 95%. It gears towards the client that may not respond at all in terms of the marketing campaign that the organizations actually wanted to post, no? Because it's all specificity, that's 95%. And the overall accuracy of the model is actually about 84%, which is not really bad at all. Okay. So specificity, 0.95, which means the model correctly classifies 95% of the actual negative records as negative. Okay, so that is why it's a 95%. No? And the model's sensitivity is about 28% of the actual positive records, which were classified as positives. No? And then the precision is about 55, no? Around 55%, 55.23%. This is actually the customers classified as positives by the model and would actually respond positively in the marketing campaign, 55.23. So the precision of your model, which will gear towards a 55%, you have a guaranteed number of clients which will respond positively. But we need to have more than 55% to be able to at least know whether the marketing campaign will actually be successful or not. Okay. And then the other values that I have discussed earlier is actually the F1 score has a value of 0.32. Okay. The F sub 2 is actually closer than your recall. And then for your F 0.5 is closer to the precision. These are compared directly to choose to be able to know what will be the best model to use. No? But of course, we're not finished yet, no, because we only have one model. Oh, we have only built one model. Now, of course, no, when we actually built a model, we need to have an accounting for unequal error costs. Okay. Now, the intrinsic assumption of model 1 was that the two types of classification errors, false positive and false negatives, are equally costly. So you can actually see there the 0.55 or the 55%, diba? So it means to say the organization will actually ask, do I need to push this through? Because I can only see 0.55% of the total clients will actually respond to the marketing campaign that we were actually intending to do, no? In terms of retail. No? And then, of course, we need to do more investigation by posting more cost or some cost. And then this cost will be associated with the various contingency. So it means to say that we have a result of the model, we will be applying costs. Okay, and this cost will give us a better understanding whether we will be spending more or we will just retract the idea of doing a marketing campaign. Okay, because it's not enough for us to be able to create a model and then follow the model because it has an high accuracy. We need to apply monetary costs so that we may be able to know whether we will be spending much or we will spending low in terms of this type of campaign. So to do that, there will be a true negative, false positives, false negative, and true positives as well. But in this case, we will be putting costs on each of these notations. So a non-responder being correctly classified, that's true negative, correct? So the retailer will not go to trouble in contacting this customer because it's a true negative. We all know that when the model actually says it's a true negative, it won't respond at all. So meaning the new notation will be cost underscore TN, that would equate to $0. Okay, or $0. Okay, because we're not going to spend an amount on this one. Okay, on these customers. No? Now, the false positive, these are actually non-responder being incorrectly classified as a responder. This is not a serious error at all. Okay, as the cost of contacting each of this customer is, say, for example, $10. No, we'll just actually give an amount. No, so the notation will be cost underscore cost sub FP equals to $10, for example, because it's a false positive. It means to say it's a non-responder incorrectly classified by the model as a responder because of course, since this is considered as a responder, we will be allotting $10 for each of those customer that was actually flagged as false positives. Now, the false negatives, a positive responder being incorrectly classified as a non-responder. This is actually sad, no? Because it's supposed to be a positive, a true positive. But since the model actually incorrectly classified this as a non-responder, we will consider this as cost sub FN, which is equate to $0, no? Or $0 because we're not going to spend an amount on this one because it's classified as a non-responder as well. Okay. Now the true positive, these are responders or responder being correctly classified. So this is 100% sure. So the retailer would contact this customer and the customer would come and spend, say, for example, an average of $40. No? Since the profit is equals to negative cost, no, we will have a notation cost sub TP, which is equals to negative 40. So you have to understand that the customer would come and spend on an average $40, no? So since profit equals to negative cost, we're actually getting towards the negative cost, no? It's always negative in this case, okay? So we will be allotting $40. Again, the cost is actually arbitrary. The reason why we have put the $10 and the $40 is for example purposes only. Since it is arbitrary, it depends on how much would the retailer would actually spend on your false positives and for your true positives. Now, to continue accounting for unequal error cost, no? So you add $40 across the bottom rows and then divide by 0. So as you can see in our new contingency table, the actual category and then the predicted category for 0 and 1 for cost underscore for cost sub TN, you have 0. For your cost sub FN, you have 4. And then for cost equals to cost sub FP, you have 1. And then cost TP, you have your 0. Cost sub TP is equals to 0. The false negative cost is actually four times higher than the false positive cost. No? So for the model 1, we have an assumption of error being equally costly is actually invalid. So we will be creating another model, which is model 2, which will incorporate unequal error cost later on. Okay. So here you have another values after you have applied the values of the $10 and the 40. Anyway, your model or the Jupyter notebook that I'll be providing will give you a better understanding on this one and on the new contingency table. Anyway, for this contingency table, you have your TN, FN, you have your FP, and then you have your TP. The new values are actually 7163 for the TN, 2451 for the FP, 618 for the FN, and then 1322 for the TP. To get the TN, the TAP, the GT, the TPP, and the TPN, all you have to do is just get the sum across for the column and for the rows. And then, of course, the GT, it's still 11554. Okay. Now, take note that when we develop the model, we will be evaluating it and we will be obtaining this contingency table. Okay. Now, because of the error costs of model 2 are unequal, you have to take note that the evaluative measures introduced earlier will now be superseded by a new evaluation method, or evaluation measurement, which is the model cost per record. So it's actually an additive inverse of the overall model profit per record. Okay, so you have to take note of that. So this one is the unequal error cost, and then the next one, okay, this will be when there is an error cost that are unequal. One of the most important thing is the evaluation measures for the purpose of model selection. Okay, we will be applying this so that we may be able to know which model are we going to choose later on. Okay, so we have different another formulas that we will be applying. This is actually for the purpose, like I've said, for model selection. So there will be an overall model costs. The overall model cost will be the cost in creating the model, not just creating the model. What are the costs that will be involved, and what will be the output? What will be the cost of this after we have made all of the things, the marketing campaign, developing the model, and so on and so forth. This will be the overall cost of the model. So the formula is actually TN multiplied by cost sub TN plus FP multiplied by cost sub FP plus FN multiplied by cost sub FN plus TP multiplied by cost sub TP. Now, the error cost for true negatives and positives are actually equal to 0 since no action is taken. So in this case, the overall model cost will be FP multiplied by cost sub FP plus TP multiplied by cost sub TP. And then you will be having model cost per record, and then you will having model profit per record. Per record, we're just pertaining per record. So there's an overall model cost, and then there's a model a cost for your model per record. Okay. So the model cost per record is actually overall model cost over your grand total, and then your model profit per record is actually the negative model cost per record. Okay, so later on we'll try to transpose some of the values there for better understanding. Now, for the model selection, you need to choose the model which actually minimizes the cost model per record, or conversely maximizes the model profit. So you need to know how much would it cost you or how much would you spend on the model per record, and you should be able to know what will be the maximum model profit. Okay, so this is very important to report the per record cost or profit, because the overall cost varies within the size of your data set. So using the cost delineated in the previous table, we will be calculating the overall model cost for model 1 and model 2, which we'll actually be creating right now. So the overall model cost for model 1, this is the formula, FP multiplied by cost sub FP plus TP multiplied by cost sub TP, which is 441 plus $10 plus 544 multiplied by negative 40, you'll be having a negative $17,000 That would be for the overall model cost for Model 1. The overall model cost for Model 2, same formula, 2451 multiplied by $10 plus 3122 multiplied by -40, that would be negative 28,370. So that would be your overall model cost. That would be the amount that you'll be spending, no, for each of the model. Now, for the profit for per customer for Model 1, the formula is actually the negative overall model cost for Model 1 over your GT. So that's 17,350 over 11,554, which will equate to $1.50 more or less, $1.50, no? And then the profit per customer for Model 2, same formula. So that would be 28,370 over 11,554, which will equate you to 2.4554. Okay, so using the cost, no, okay, based on the two equations, you would be able to see there's a difference between the profit per customer for Model 1 and Model 2, which is $1.5 and $2.4, no? Okay. So we increase the retailer's profit by almost a percentage from accounting of your unequal error cost. Okay. So that would be your profit per customer. So meaning you have a little bit of profit if you're going to utilize Model 2. Okay. So it's about roughly kung 1.5 is that, if that's 1.5 1.5 2.4 that would be around more or less $1. You'll be having a 9.9 in a way profit, no, if we're going to use Model 2. Okay, of course, no, in this era, no, if we're actually using business in businesses, no, we're actually using big data. And of course, when we're talking about big data, we always use this as a leverage so that all of the information, okay, exists in our database, or the database that the company or the organization actually utilizes, no, would be able to help us, no, uncover optimal prediction of the models, no, that we're actually using, no, or creating, no. So in other words, as an alternative to assigning error cost, no, because these cost values seem right, no, or that's how we have always modeled them, no, we would instead be well advised to listen to the data itself. Kaya nga siya data-driven error cost. Before, the error costs were actually just defined, no? But in this case, we will be gearing towards the use of data, no, to be able to drive what really is the error cost for each of the model. Okay, so we would like to illustrate, of course, the power of data-driven error cost by, creating another model, which is Model 3. Okay, so if you may recall, no, you have a non-zero cost. For the cost sub FP, you have $10, and then for the cost TP, you have -40. Okay, so that's non-zero costs. Okay, now fortunately, no, however, we have access the data, okay, that would give us a better understanding or an idea of the cost sub TP, okay, which is the sales per visit, no. So this predictor will provide us the average amount of money that we will be spending per visit for each of the customers. Okay, so if we calculate the mean of the sales per visit across all of the customer, okay, the mean of the sales per visit, no, we could use this as a better estimate, no, for how much of the customers would come and spend on a daily average, no. So the previous estimate was actually 40, correct? But the mean sales per visit record training data set is around $113.58. Ito yung sinabi ng data because of the data-driven analysis. No? Previously, 40%. That's an assumption. But the mean sales per visit, ang sinasabi ng data nyo ay 113.58 instead of 40. So we'll be changing the negative 40 into $113.58. Okay? Our data-driven cost for the true positive will therefore be notation cost sub TP will be negative 113.58. Okay? So, no analogous data for us to estimate the cost FP, so it will remain $10. Okay? So we will be revising our contingency table. Okay? So, subtracting the cost TP, again, negative 113.58 from the bottom row and dividing each of the cell by $10, which will gives us the data-driven cost bago na yung contingency table natin. So the actual category, predicted category, cost TN 0, cost FN 0, cost FP $10, cost TP that would be negative 113.58. So the predicted category again, cost FN and so on. So we will be having a TN, FN, FP, TP. 4237 for the TN, 5377 for the FT, FN 201, TP 1739. So again, all you have to do is to get the TAN, the TAP, the GT, the TP, and the TPP. All you have to do is just add them all up, based on columns and rows and so on. Okay, so we will be developing. As you can see that the false negatives are actually 11.358 times costly as the false positives. No? So the model 3 is developed, which is evaluated using a test data. Okay, the profit per customer for model 3 is around $12.4412. Okay, that will be for your model 3. So as you can see there, there's a great increase in profitability compared to the previous model, Model 1 and Model 2. So much of this increase is actually due to the data-driven increase cost that we have actually adjusted from $40 to $113.58. So comparing all of these models accordingly to the new costs, model costs. Okay. So there's a significant change in terms of profit per customer because of the Model 3. That's $12.44, no? Medyo malaki siya. Now, taking time to evaluate model, or different models, as you can see there, Model 1, no error costs, because we have not applied the error cost yet. For the Model 2, there is an error cost adjusted 4 times and then 4, okay, and then the Model 3 error cost adjusted into 11.358. No? So, as you can see, the model evaluation or evaluating the models for 1 to 3 with the best performing model result is actually in bold. No? So that would be on Model 3. Okay. Now, take note that Model 1 is the least profitable model kasi without error cost siya, no? Is the most accurate naman siya at about 84%, no? While Model 3 is the most profitable model applied with the data-driven error cost, at least an accurate model of around 51.72%. Now, the thing here is that even though you have a very high accurate model and then you compare that to your Model 3, which has about 51% accuracy model, you need to refer to the overall model cost and the profit per customer. Okay? So it doesn't mean that even though you have a high accuracy model, you will be gearing towards the use of a high accurate model. It doesn't it doesn't equate there. No? So even though you have a very high accurate model, but you're spending a lot, and then you'll be gaining less. So you might as well utilize a low accurate model, but you'll be having a more profit in exchange. Okay. So I think the overall idea here is to be able to comprehend that we don't just gear towards the accuracy of the model. We always gears towards the other side, which is the profit. No, the profit on how much cost that we're going to spend in terms of creating the model, and how much are we going to have in return, no, as a profit. Because at the end of the day, companies are actually after not just spending money, but also earning more money, no, instead of spending more. Okay, so that is why model 3 is the most profitable model, and then, well, of course, is the least accurate model. No? Now, accuracy is not the proper metric to compare models which have an unequal error cost. Just take note that we're actually talking about unequal error costs. We're not actually gearing towards something that has a value on it. Now, you may be asking, how are you going to put an error cost if you're actually just detecting, like for example, vehicles, or you're just detecting something? Of course, you will not actually apply an unequal error cost, because there's no error involved, or there's no cost involved, no, by just merely counting how many cars or how many motorcycles actually passes by in a certain area. No, you only apply unequal error cost and the data-driven error cost if you have cost involved. Like for example, in retail, if you're selling something or anything that has value, monetary value on it. Okay, so you just don't gear towards accuracy. It's not a proper metric to compare models which have an unequal error cost. Now, sensitivity was more important than specificity. The recall is actually more important, no? Rather than capturing the non-responders. So it's more on getting towards who will actually respond, no? And how many people will actually respond in terms of the marketing campaign. Okay? So, that's it, no? So the best performing model had the highest sensitivity, while the worst performing model has the lowest, no, had the lowest sensitivity. No, the reverse relationship actually held for your specificity. Okay. Now, precision did not appear that very important, no, either way, as using your model 1, which has a solid precision. For the F2, which favors recall sensitivity over precision, was highest with model 3, while F sub 0.5, which favors precision over recall, which is actually highest on model 1. Okay, so I think we should also make sure that the models outperformed the baseline model. So there's always a baseline model. Now, like I've said, being a data scientist should always evaluate the models and apply different metrics in terms of evaluating classification models. No? And here, I think we have also discovered error costs were not always equal when unequal model cost per record may be used as the best metric. No? And also there's an illustration on how data-driven costs can be further enhanced, no, in terms of profitability. And of course, after we have classified and evaluate our models, we will be able to have at least an overall picture on what model to use, no, in terms of this problem. Okay.